Hello students, welcome to lecture 4, entitled as Feasibility of Learning. In our previous lecture, we discussed different types of learning, which included binary classification, multi-class classification, regression problems. We also have seen different protocols of machine learning, which we call as batch learning, online learning, or active learning. We also have seen examples of supervised learning, unsupervised learning, semi-supervised learning, and also briefly discuss about the reinforcement learning. We later clarified different types of features that we can work with, one of which we called as concrete feature. We also talked about raw features and abstract features. Today we have a new topic, which we call it as the feasibility of learning. By learning, we mean the machine learning. First, we'll answer the question, if learning is possible at all. Right? To answer that question, we use some techniques from probability theory. Here, you may need to refresh your probability that you have studied before. And we will show that connections of this probability to learning and to real machine learning problems. Given 6 examples of these different patterns, square shaped, we label the top row as -1 and bottom 3 examples rows as +1. Now I can ask you, given these labeled examples, just look at it, at those different patterns, and learn from it. And now, assuming that you have learned, I ask you to find the correct answer to this new unseen example. What would be the label, +1 or -1? You have estimated your G based on this given limited amount of training examples. Take a moment. Well, you can try to seek the similarities between these dark or black shaded rectangular squares inside this object and see if they are similar. Is it 1, +1, or -1? We may have 2 different answers. So based on these 6 examples, we give one test example, and then you can say this is the output would be +1 or -1 because of the following reasons. It could be +1 because if you look at the symmetry of these patterns. So here we see some symmetric patterns. For example, this one symmetric, another one, shapes are symmetric. Or just count black or white counts are equal in 3. So 3 black counts, right? And 3 white count. Or black count equal to 4 and middle top black. Middle top black here, black here, black here. Also here we have a black one. You can also say it is -1 because of the following reasons. Left top black is -1. Middle column contains at most 1 black and right top. The main question here is which one of them is really true, +1 or -1 for the given example, right? Does your G that you have learned from 6 examples approximate the ideal target function? How can we make sure that your G approximates our target function? All of these reasons are valid. However, your adversarial teacher can always say you didn't learn. Let's take a look at this simple binary classification problem. So here in this example we see data corresponding to 5 different examples of binary value. Each example has 3-dimensional feature. Each feature is 1 or 0. And then we have the labels for each example in the forms blue circles, red cross, blue circle, blue, red cross. And assume that these labels were generated by target function. Okay, these are given beforehand to our input space, input data, three-dimensional, and the y given by target function. This is a supervised learning problem with the binary classification task. We can enumerate all candidate functions as h in this case. So now assume that you use perceptron learning algorithm and select your g from the entire set of h, and assume that this is a simple linearly separable dataset. And you make sure that your final selected perceptron agrees with all given true answers or labels for each example, right? And then the main question is, does G approximate F? How can we guarantee? Does it mean that if you learn from the given examples and make sure that the selected perceptron or any kind of G function, if it agrees with the labels or true answers, does it mean that we have a function that makes no mistakes on this dataset and approximates our target function? Here we can see that given the dataset with their provided labels or target values, we can always find the G or learn the G from the data using some simple mistake correction techniques such as we have seen in the perceptron learning algorithm, and try to approximate the target function. So to the question whether G approximates the target function F, we can surely answer that inside the dataset yes, because assuming that all this has been generated by target function, we can find G from the data and make sure that it approximates target function for each given example. Now assume that we have 3 new examples outside the training dataset. So we usually call them as test data examples or test set. And in this case, we don't have y's. We don't have access to y's. This data is not labeled. Using the learn G, can we accurately identify its labels, whether this is the blue circle, red cross, or blue circle, or all different possibilities? Because here we have the binary classification problem, which we can have up to 8 distinct possible labels for 3 examples, right? As a result, we can have 8 possibilities. So target function 1 could have labeled all 3 examples, all circles, blue circles, or these labels or that, up to 8 different possible combinations. Now the question is, does our G approximate F, our target function? Well, inside yes, but outside the dataset no. There is no way to guarantee or make sure that the answer provided by G will be equal to one of these 8 possible target functions. But that is what we want. That is the core question in machine learning. We want to estimate the G, learn from it, learn it from the data that will approximate target function F outside the data. So, unfortunately, learning from data is doomed if any unknown F can happen. No free lunch theory in machine learning states that learning is generally impossible. Learning the G from the data that approximates the target function outside the data is impossible, as G, the labels for these given 3 examples, could be one of the possible 8 distinct combinations. And there is no way to prove that if, assuming that the G, if it is F2, then it is a true target function and not the F5. Therefore, we need some assumptions in machine learning to answer the question of the following form. Does G approximate F outside the dataset? Here we have another fun time or quiz. This is a very popular brainstorming problem with the claim that 2% of the world's cleverest population can crack its hidden pattern. I believe you have seen these kind of problems sometime in past. For instance, like given one example, the sequence of numbers 5, 3, 2, and then with the y, right? This is x and this is y. I ask you to learn from this example and then try to come up with the output to this test example inside the given data. This is the unseen example. So can you generalize or generate output for this? So here it's like a learning problem with one example. X is 5, 3, 2, y is 15, 10, 22. Okay? So learn a hypothesis from the one example and predict on X test example. What is your answer? Take your time and try to figure out the correct answer. What is clear is that there is a designer or someone who have come up with the following relationship. Okay? Some person probably has a formula that will give us the following mapping, and it can be our target function, right? And then we need to come up with some reasoning that will give the answer to the following question. Here the reference answer is 4. There is no correct answer. Why? Following the same nature of no free lunch theorem discussed briefly, we can't hope to be correct under this adversarial setting. However, we can see that number 2 is a designer's answer, and then we can provide some simple formula. So first 2 digits of these are equal to 5 times 3 is 15. And next 2 digits are equal based on the following formula. So x1 to x3 multiplication. So it gives 10. And then 22, the last 2 digits could be explained with the following simple formula. x1 times x2 plus x1 times x3 minus x2, which will give us 22. And we can also come up with different formulas that may give us the following answer. Or you can also say, I need more examples to get the correct answer. Well, no free lunch theorem again states there is no way to prove that there is one unique answer to this problem. We mentioned that it is difficult to infer unknown target function outside the dataset in machine learning. Well, is there anything similar? Other scenarios where we could deal with something unknown? Well, let's take a look at the following example. Consider a bin of many orange and green marbles. Now we can ask the question, do we know the orange portion? Probability of the orange portion of the marbles in this bin. The answer would be no. Can you or can we infer the orange probability? Yes, we can try to infer the orange probability in the bin. For that, we perform some simple experiment. We have a bin, we take a sample out of the bin and repeat this procedure several times. Now, let's assume the orange probability is equal to mu. Then, green probability will be 1 minus mu, with mu unknown. We take or sample n marbles independently with orange fraction equal to nu, and green fraction will be equal to 1 minus nu. Nu can be calculated from sample of the data. So that means we know nu. Now the next question is, does in sample new say anything about unknown or out of sample mu? It's out of sample because this is sample. Whatever inside the bin, the orange probability is, as we said, it's equal to mu. We can give two different answers to this question. Does in sample new say anything about out of sample mu? We have two cases of answers. First, no. First answer is no. Possibly not. Because sample can be mostly green while the bin is mostly orange. This could happen, possibly. And we can say yes, but yes with probability. So we could say probably yes, because in sample new likely close to unknown mu probability of orange marbles inside the bin. So formally, the question here is, what does nu say about mu? Is there any relationship between nu and mu? Can we infer mu probability using nu? First, in order to answer that question, we can do several experiments. We sample a marble from the bin many times, and then we can estimate the probability of nu, probability of orange marble in the sample. And our unknown will remain the main goal to identify. So mu is orange probability in the bin. It has been shown by Hofting that in a big sample, when the sample size is sufficiently big, so nu is probably close to mu within very small fractional number. So probability, in other words, of nu being different from the nu by some small tolerance is upper bounded by the exponential function. So 2 exponential of 2 epsilon square n. This inequality is called as Hofting inequality and can be used for similar situations, for marbles, for coin flipping, for estimating the polling results from a sample data. So the statement using the Hofting's inequality and claiming that nu is equal to mu is called probably approximately correct or PAC learning. Again, the Hofting's inequality gives us this right-hand side bound, which depends on some sample size. And our interest or the question is on the left-hand side, the answer to our question. Probability of these two being different by a very small number is upper bounded by the exponential function, negative exponential function. So this is basically a decaying function. So if we make the n large enough, we can make sure that the probability of this event is very small, right? Then we can say that nu approximates or nu tells something about mu, all right? So the proof for this inequality is in the textbook, Learning from the Data, and is about 2 pages. If you want, you can take a look at the details. But for us, in this case, the important is that we can use this Hofting's inequality to answer the question of, can we infer something unknown? So Hofting's inequality is valid for all possible n's and then epsilons. And it doesn't depend on mu. We don't have to know mu, okay? We just have to make sure that the right-hand side inequality is small enough. For that, we have 2 parameters. If we can call it as parameter, epsilon and then number of marbles, in this case, sample size. So larger sample size or looser gap or looser difference between these two will make this side of the inequality small, very, very small. This is for higher probability that nu approximates mu. Probability of mu being different from nu by some absolute value is, very low. So Very low means if you have these sides very low, then we can say high probability of mu approximating nu. So by just looking at using the Hofstad's inequality, we can conclude that if you have enough number of examples, samples, okay, we can probably infer unknown mu by just using known nu, right? We can probably infer unknown mu by known nu. So we considered the bin scenario. We wanted to find out the probability of orange marbles in the bin. And let's now try to map the relations between bin and then machine learning and try to find the connections. So unknown orange probability in the bin case is similar to a fixed hypothesis. Given some fixed hypothesis, we want to know if that fixed hypothesis is our target function or not. The marbles in the bin is similar to the training examples in the machine learning case. These are the input data. The orange probability can be considered as the fixed hypothesis is wrong on given input. So h of x is or doesn't agree with f of, while the green marbles case is h is right. So the select hypothesis is right. So it agrees with target function. Sampling n marbles from the bin according to IID assumption is equivalent to checking the fixed hypothesis on all training examples with also assumption that the data is identically independently distributed. So this is what IID stands for. So now, given this connection, we can say that if we have enough number of training examples distributed identically, independently, we can infer unknown probability by known fraction. So in the context of learning, machine learning, given the fixed hypothesis and many examples, a lot of training examples, we can infer the case where our fixed hypothesis doesn't agree with the target function. So this is a Boolean, let's say, function that gives true and false if these two agree or disagree. By known fraction, so fraction means in supervised case we have y's. So if you have huge amount of training data set, we can probably again infer something unknown. So unknown that our hypothesis will not be equal to target function on this example. And pictorially, this is our bin, and each marble can be considered as one training example. So we take a lot of training examples and then check whether our hypothesis disagrees with the target function or agrees. Now let's take a look again at our flowchart. Here we have new components. So first, let's take a look at this. So we assume that our data is generated by some unknown probability distribution according to independently identically distributed assumption, IID. So all of our examples are data points are generated by some unknown. Here we have our learning model, learning algorithm, hypothesis set. According to the Hofstad's inequality, we don't have to bother learning algorithm or hypothesis set. We just select one fixed hypothesis, okay? One fixed hypothesis, and make sure that your training data is huge enough, and then you can check whether your fixed hypothesis is equal to target function, will approximate the target function. According to Hofstad's inequality, again, if you have a huge number of training examples, the right hand side of the Hofstad's inequality will be very small. Therefore, the probability of h being different from the f by some epsilon tolerance will be quite small. So we can put it here. So for any fixed h, we can probably infer unknown out of sample error by known in sample error. So the out of sample error is the expectation function where we don't know this p. We don't know the probability distribution function. our fixed function, okay, fixed hypothesis, and target function or target hypothesis. Well, by known, we call it as in-sample error, E in, can be calculated. So 1 over n examples, n training points, sum across the disagreement. So this is error or mistake, right? Our hypothesis doesn't agree on some specific point with the given y label. So this is again the Boolean function. If this is true, then it gives 1, otherwise 0. Let me clarify this out. As I said, out of sample error. It's a function that gives us the difference between current fixed hypothesis and target function. So let me go back to earliest example where we talked about in sample and out of sample. So we said G approximate inside data set for sure. G approximating F is assessed by in sample error. Well, here G approximating F outside D is, we can call it as out of sample error, the difference between G and F. Out of sample error is difficult to calculate because we don't know the true labels. But according to Hofstee inequality, if you have huge number of training examples, the G will hopefully approximate F outside the dataset using a fixed hypothesis. We can use Hofstee's inequality to give a formal guarantee as follows. For any fixed A hypothesis in big data, okay, our training examples are huge, in sample error is probably close to out of sample error within some small epsilon. So if you make slight modification to the Hofstein's inequality by replacing mu and then nu by in sample error and out of sample error, we will have same bound. So here we're interested in the probability of in sample error being different from the out of sample error by small number is upper bound by negative exponential. As long as n is huge, is big, the probability of this event will be small. Okay, it's similar to the bean analogy and is valid for all n and then epsilon. Also, it doesn't depend on out of sample error. We don't have to know the out of sample error. We just have to make sure that this side is small enough. We don't need to know out of sample. F, target function, and then probability of data, probability that generating data can remain unknown. Okay, out of sample error can remain unknown. And in sample error being equal to out of sample error on a fixed H hypothesis in this context is also called as probably approximately correct. So PAC. So we can summarize. So if in sample error approximate out of sample error and in sample error is small, in sample error is small, then out of sample error is also small. That could mean that our fixed hypothesis will approximate target function f with respect to some probability. This guarantee is very important, as we can have hopes that a fixed hypothesis can approximate something unknown, our unknown target function, as long as we have huge number of examples. However, using the Hofstein's inequality, so far, we were talking about one fixed hypothesis. For any fixed hypothesis, when data is large enough, we said that in sample error could approximate out of sample error. In this scenario, can we claim good learning, good machine learning, selecting the G that approximates target function f? We can give two different types of answer. First, yes. If in sample error for this fixed hypothesis is small, then we can say A pick this one single fixed hypothesis as G. And then we can claim PAC learning, probably approximately correct. So the selected G, approximate target function. Or we can also say no, we cannot claim good learning because A is forced to pick the fixed only single hypothesis as a G, right? Even though in sample is never small. So if in sample is not small, then we cannot say that target selected hypothesis approximates the target function f. So we cannot claim PAC. Okay? Well, in the context of machine learning, we need to make sure that the algorithm makes choices, like in the perceptual learning algorithm. So it selects one hypothesis, checks if that hypothesis makes mistake or not on the given example, and iteratively selects a lot of other hypotheses. So in real learning, algorithm should make choices in the very big pool of hypotheses, not based on the one fixed h function, okay, rather than being forced to pick one. So we can call this not learning, but verification of one fixed hypothesis using the Hofstee inequality. If you take a look at our verification flow, what we have here, our algorithm that is supposed to make choice based on the bigger hypothesis is gone. We only have one hypothesis, right? And then some huge amount of training examples, unknown target function, unknown distribution, probability distribution. So this is basically the verification flow. Now assume that one hypothesis. Can you use historical records from the bank in the credit card approval application to verify one candidate formula? Would that make good decisions? If we use data from the bank for credit card approval application, then we're not learning any hypothesis. We're just using one fixed formula to verify whether it approximates our target function. So here we don't see any pattern of learning. We can consider multiple hypotheses and try to extend the Hofstee inequality to multiple bin cases. First, let's consider M hypothesis and M bins with marbles in it. We also have M out of sample errors and in sample errors. That is calculated using the sample data. So like perceptron, in this case, we want to be able to select one out of M hypotheses for each different bin, and for sampled marbles, we'll have different in-sample error for a single fixed hypothesis according to Hofstee's inequality. Similarly, for second bin, we'll have another hypothesis, another fixed hypothesis with corresponding sample error, and another bin and another hypothesis. So Hofstee inequality allows to verify whether H1 approximates or similar to the target function under the condition that the sample size should be big enough. Well, if we extend to multiple bin case, we have different in-sample performances and different hypotheses, and like in perceptual learning algorithm, we select the one with the smallest in-sample performance. Extending it to multiple bin cases will work like perceptual learning algorithm. For instance, we have M hypothesis again, so our target will be to select the hypothesis which provides us mostly green marbles. For instance, out of M, we will select the best H. Right? So for instance here, okay, so green marble represents that our selected H agrees with the target function, unknown target function. So while out of sample error remains unknown, we can calculate in sample error. So in the bin case, out of sample error can or be represented as mu, while nu is in sample error, right? So by just visual looking at this, H2 is better than H1 because most of the marbles are green, and H2 seems to agree with target function. In sample case also, more greens. But eventually one of the hypotheses will get us all green. If one of the hypotheses gets all green, we simply select that hypothesis and then declare that our HM, for instance, approximates target function. However, there is a problem with this selection, and Hofting inequality may not work or be valid when we extend to multiple bin cases. Let's take one example, for instance, to clarify why selecting this hypothesis is not a good idea or a valid choice. So, to clarify that, let's consider a coin flipping game. And instead of green or orange marbles, let's think that we're flipping the coin, which has same binary decision. So this is the outputs of green or orange marbles, which represent heads and then tails. So assume that we perform M experiments with the coin, right? So a question: if everyone in, let's assume size of 150 students in the class flips a coin 5 times, and one of the students gets 5 heads for her coin called G. It's a fair coin, right? Then the question: is G really magical? How is it possible to get all 5 heads while the coin is fair, right? We should not expect it. The question is no. So even if all coins are fair, the probability that one of the coins results in 5 heads in this experiment is very likely. So 1 minus the following is, well, very highly likely. So we can consider those kind of cases as a bad sample that doesn't represent the true distribution of the coin flipping experiment. So in the context of learning, bad sample it can be explained as a difference between in sample and out of sample. So getting all heads, all right, could be linked to getting in sample error 0 and out of sample error all other events. All right, so this is also a problem related to selection bias, so-called, which involves choice. So we will have such bad samples, okay, and also bad data. For instance, our in-sample error for selected hypothesis is perfect, all 0. However, out of sample is 0.5, right? 1/2. So bad data will contain a lot of bad samples for one selected H. Let's consider this case. E out and in is different. So we consider that case relating to a bad sample. All right, so out of sample error is big, far from, that means target function, but in sample is small. Correct on most examples, on all examples. So if you have our hypothesis, if you just list it as it is, so we have several cases of bad samples in a given data set, and we need to extend the Hofting inequality. So Hofting is based on the bad event, right? Upper bounding the bad event by some exponential function, negative exponential function. So for this selected H, the Hofting will be probability of bad data or sample happening will be equal to the sum of all individual bad samples, okay, in the data. So this is, again, we consider all these. And next we need to define this next side of right hand side of this inequality later. But before that, let's consider not one hypothesis but M hypothesis as listed in this table. So this is equivalent, like we will have M hypothesis, and there will exist one or some of them, some of these H, such that our out of sample error will be different from in sample error, or they will deviate much. So probability of bad sample error in Hofstein's inequality was that these two are different. Let me open that slide real quickly here to show you. Here, I just copy and paste. This is the Hofstein's inequality for one select hypothesis. So we will have a lot of these bad samples, okay, for M hypothesis. A lot or some of them, okay? So if we list all of these given data set that we have and hypothesis, we'll have bad sample, okay? And then we sum all the bad samples, and then we extend to M hypothesis. So if we consider all the space of hypothesis, then we can also consider the bad samples across all different hypotheses, M hypothesis, and for across all data points, across M hypothesis and across all data points, right? So we have the bound of bad event, bad data for all M hypotheses. So as follows, let's look at this. So probability of bad event is equal to the probability of bad event for H1, bad event for H2, bad data or event, I call, or up to bad data for HM. So we can just call it, take the union bound of each individual probabilities for each M hypothesis. So probability of bad for one first hypothesis, or probability of bad data for H2 and bad data for HM. This is called a union bound in probability theory, right? And then what we do is simply we apply Hofstein's inequality for each H hypothesis. 2 exponential, okay, first hypothesis, second, third, up to M. So this will be equal to the sum will be equal to 2m exponential and negative 2 epsilon squared n. So the extended Hofstein's for multiple hypotheses can be written as 2m, okay, considering the all worst case scenarios. And so this case, a finite bin version of Hofstein, again valid for all m, n, and epsilon. And it similarly to the single bin case, it doesn't depend on out of sample error, right? We don't need to know out of sample error. Plus target function and probability distribution can stay unknown. Okay, again, this is in sample being equal to out. So sample is probably, okay, the probably means this side, right? Probability. This is a probability value. Probably, approximately is probability of in sample being different from the out of sample greater than some epsilon. Okay, and the algorithm will pick the H, we'll aim to pick the h with lowest in sample error as g in this case. If you look at the extension of Hofstein's inequality to M hypothesis, there are some things that we need to emphasize. So one of the things is that the h, the set of hypotheses in our flowchart, should be finite. That's one of the conditions. And if n is large, for whatever g picked by algorithm, out of sample error will approximate in sample error. Then if A finds one of the g with smallest error in sample error, then probably approximately correct will guarantee that out of sample error will also be 0 or approximate 0. Now we have extended the Hofstein's to multiple M cases, M hypothesis, right? And what if M is infinite? Okay, the hypothesis tends to infinity, like perceptrons. What could be the situation? Think about it, especially this part, right? 2M. What if M is infinite? That will be the subject of the coming lecture, the answer to this question. So in this lecture, we try to answer the question whether learning is possible. Okay, we have seen that about our hypothesis being equal to target function outside the dataset, or approximate target. And we try to formulate a probability-based answer to this question using the well-known inequality called Hofstein. We consider the bin experiment, bin situation. For instance, we ask, do we know the probability of mu, or can we infer probability of mu from the sample nu? We try to link the connection to machine learning and to real learning.